class. Onya. Onya, est-ce que tu es là?
Oui,
Oui. Est-ce que ça va?
oui, ça va bien, merci. Et
Tu
vous?
es à Moscou ou tu es chez toi?
Ah, je suis à Moscou, dans le campus à Dolgoprodr.
Alors, comment ça va à Moscou?
Il
Pour
fait froid,
une
bon.
fille, bon, c'est un pays assez loin,
Oui, très loin.
très loin. Mais, est-ce que ça va?
Oui, ça va bien.
Très bien. Bon, now, now we will speak English. Excuse me. Oh, yeah. So we want to finish our file seminar number 1. I've sent you 2 files, seminar number 1, corrected because it was some mistake. The presentation now it's corrected, so we can start. Please find page number 9. Is it good? Page 19 from the file seminar 1.
It would be the page about the definitions of the least
Yes,
and
yes,
upper and greater and lower bounds, correct?
exactly. So, dear colleagues, we want to discuss some, I say, some bounded sets. You can imagine that if you have an interval 0, 1, then all the members of this interval are less than 1, and they are also less than 2, 3, 4, 5, and so on. I hope it's clear. But the members of this interval are also greater than 0, -1, -3, -55, and also. So the question we want to study is the upper and the greatest lower bound. This means, you see, as for the page 19, we have the first definition, the least upper bound. So, as for this definition, the number b is a least upper bound for a set M. If you take your interval 0, 1, you have that all of x from this interval are less or equal b. It's clear. So as for this interval 0, 1, a closed, if you want a closed interval, so all the real numbers from this interval are less than 1. They are less than 2 also. They are less than 3 or 4, but we can prove that the least upper bound in this case is 1. And this upper bound coincides also with the maximal element of this set. For example, if you take an open interval 0, 1, so excluding the point 0 and 1, then you will have that the least upper bound in this case will be also 1, but this element is not from your open interval. This is why, this is the reason to introduce the upper and then the greatest lower bound. Because we know that there is only one number due to this definition, such that you see all the numbers of my interval are less or equal to b. But if I take each epsilon positive, then due to this definition, I can find an element from our set M such that x is strictly greater than b minus epsilon. In the same way, we define the greatest low bound. So all the numbers of our set M, because we are dealing with the real numbers, in fact. So all the numbers are greater or equal to A. But we also know that due to this definition, for each epsilon positive, we can find an element x from our set M such that x is strictly less than A plus epsilon. So page number 20, let us consider some illustration for this definition for the upper bound. So we have, you see, as for this picture, we have sup M. We have set M before some point, I don't know what. So we have a number of upper bounds of M. I repeat, if you have, for example, in this case, the interval 0, 1, you have the upper bounds of M. M is 0, 1. So you will have 2, 3, 4, and so on. Is it clear?
Yeah, it's clear.
Yes.
Clearly.
Yes.
Clearly. Yeah. Very good.
It's clear.
So now we turn the page and we try to consider some page 21. We try to consider some examples. So if you see, if you have an infinite interval from 1 to infinity, can you explain me what this infinity?
All positive numbers, like all the way to the positive, no
So
ending.
you have something, yes, you have something like natural numbers with number n which goes to infinity. So any number, but the number infinity does not exist. You see? So it is not a closed interval. It is an open interval. So if you have, for example, the interval 1.n, where n is a natural number, I don't know, 1,000, 2,000, and so on, this is a bounded interval. But if we write like this, 1 infinity, this means that it is a part of real axis. You see, a part of real axis. So it is an infinite interval. Then you see, we cannot find a number for this set which bounds this interval above. However, if you write this interval like this, you have a number 1, which is a lower bound. And moreover, if you take into account your definition of the greatest lower bound, then you have that the infimum of infimum is 1. So all the numbers of your set are greater or equal to 1. You see, there is a number of lower bounds, but the greatest one is 1. Then we can consider the second example, m, which is 0, 1, but where 1 is excluded from our set. So 1 does not belong to our interval. In this case, we see that the maximal element, there is no maximal element, but we can say that the sup of this set is 1. So all the elements are less than 1, but this element does not belong to the set M. However, if you take 0, this will be the minimal element of the set, and also the greatest lower bound of this set. Is it clear? What do you think about?
Yeah, it's clear.
Is it clear? Really?
Yes,
Yeah, it's
clear.
clear.
Okay, so you see, you have some bounded sets. Maybe they are bounded from above and below, but also it can be that we have some sets which are bounded from above and not bounded from below, and so on and so on. We have some situations. So this third example, please. The third example I have, I think that you know the notion of a sequence from your lectures. You know. So I take a sequence. 1, 1 over 2, 1 over 3, 1 over n. And n is a natural number. So this set is not an interval, but some points from an interval 0, 1. You see? And n, I think that I hope that you know that if n goes to infinity, it will be 1/3, 1/5, 1/6, and so on. So this sequence, in fact, this sequence goes to 0. Then you see that if I take the set M defined in the example number 3, then I will have the maximal element of this set, which is 1. And this element is also sup of the set M. But as for the inf of this set, you see, we can say that as n goes to infinity, then the general term of my sequence goes to 0. Clear? Is it clear? Because
clear.
because we have something 1 divided by n, and n may be rather large. 1,000, 2,000, 3,000, 1 million, and so on. So we hope we will see this by defining the limits of a sequence. We will see that as n goes to infinity, so we take rather large n, then we will be in our set near 0. But we cannot take 0 because it is only the limit. So but we are near 0. Then we claim that 0 is the inf of this set, but 0 does not belong to this set. So this is why, you see, I say that we have sup of some set M, and I say we have inf of some set M. Really, in our real life, we have the maximal and the minimal element, you see. But in this case, I have something which can be the minimal element, but this element does not belong to the set. This is why the mathematicians use the term of inf or sup. Is it clear?
I mean,
The guys, is it clear? The girls.
Yes, it's clear.
Why you see, the question is why we have to define these notions of sup and inf. This is exactly because we cannot say that there is an element which is greater or which is less than of the elements, but we want in our hands to have something which corresponds to the maximal or the minimal element. And that is why we introduce sup and inf. Clear? Or maybe you have questions. Because
it's clear for me, yeah.
Because these notions are very important in our further analysis. So please, if you have questions, if you do not understand something, please, maybe you have stupid questions. No matter. We can discuss this because in the beginning, it is always like this. You have to understand. If you close your eyes and you try to imagine these notions, you can see this. If you cannot see this, please ask the question. No question. Clear or not?
Yeah, it's clear.
Onya, clear? Clear.
Yes.
Good. So we turn the page and we start to discuss some exercises. Page 22. So the first exercise for upper and lower bounds, which is exercise number 15, we want to find SUF and if inf of M is if the set M consists of elements that are the members of the sequence X sub n with the first case. We start with the first case. If X sub n is 1 plus minus 1 to the power n over n, and n is 1, 2, and so on, so n is a real number. I hope that after your lectures, you understand that as n goes to infinity, the second summand here goes to 0 in some way. So if we take n 5,000 or 6,000 and then 1 million and then 3 million, then you have rather small term, but the sign of this term for these terms, the sign is rather different. Why? Because of the minus 1 to the point or to the power n. So you see, in this case, in the first case, I try to write some first terms of our sequence. So you can see that it will be 0, 3 over 2, 2 over 3, 5 over 4, and so on and so on. So attention. If I take a number n, which is 2k, where k is a natural number, then I will have for my sequence that the member of my sequence will be 1 plus 1 over 2k. You see, as for the second term of my sequence, if I take in the definition xn 1 plus minus 1 to the power 2 over 2, then minus 1 to the power 2 is 1, and I will have 1 plus 1/2. So the second term of my sequence is 3. I hope no problem with the operations, with the arithmetic operations. No problem.
Mhm.
Clear.
Mhm.
really. Then, if I take, you see, so for n equals 2k, where k is the natural number, you will have something which is greater, really greater than 1, because we have 1 plus something positive. Yes? But if I have n, which is n equals 2k plus 1, so you will have 1 minus 1 over 2k plus 1. So this is something which is less than 1. You will see, when during your lectures, as for the limits of the sequences, that in fact, when n goes to, it is something like a remark. It is not necessary to see this now, but if you take n goes to infinity, then the limit of this sequence will be 1. The limit of the sequence will be 1. Then, if we take our sequence, which is given at this page 22, then we will see that the maximal element of this sequence, will be 3 over 2. Why? Because of other elements due to our definition are less than 3 over 2. Then the minimal element of this sequence is 0. This minimal element, when we take n equals 1, n equals 1. You see, minus 1 to the power 1 divided by 1 is minus 1, so we have 0. So all the elements of the element are positive, but we have an element which is 0 in this sequence, and we have the maximal element which is 3 over 2. So in this case, we can claim that sup of this set of this sequence is 3 over 2, and the inf of this sequence is 0. Is it clear, the guys and the girls? Or you have some questions?
Yes.
Yeah, clear.
Clear. Thank you very much. So we turn the page, and you see here you have an exercise number 2. You have that x sub n is the sum of 1 over 2 plus 1 over 4 plus 1 over 8, so on, 1 over 2 to the power n. So you turn the page, okay? You turn the page. In this case, we have a geometrical progression. So, attention, in this case, it is not like in the first case when we have some discrete numbers. Here, for any n, x sub n is the sum of n terms. You see, is the sum. in this case, you know from the first part of the lecture or of the seminar, excuse me, you can see that it is a geometrical progression. So in this case, you have to know, you can consider our notes, our file. So you can find the sum of these and terms. And I write that xn is a in a general case, a multiplied by 1 minus r to the power n divided by 1 minus r. In our case, the first term, you see, the first term a is 1 over 2, 1/2, okay? And r is also 1/2. So we can find that the general term of our sequence x sub n is, it's the formula 4.1. You see, it's 1 minus 1 over 2 to the power n, to the 1 minus 1 over 2 to the power n. So if you want, if you know the definition of the limit, you can immediately claim that this sequence goes to 1. So, but as for the sequence, as for the sequence, point 1 does not belong to our set. But as for the minimal element, you can see that the minimal element is 1/2. So nth of this set M and also the minimal element of this set is 1/2. However, we cannot find the maximal element of this set, but only supremum of the set, which is 1. Is it clear, the guys and the girls?
Yeah, it's clear.
It's clear. So now we can explain a little the statements of our exercise. So you turn the page, and we consider page number 24. So first of all, in the first statement of our 4.2, let's consider the first statement. The first statement is that the inf of M, or the minimal element of M, is 1 over 2. You can see that our sequence we will consider this fact later, but now for any x sub n plus 1, it is strictly greater than x sub n. So any next element is greater than the previous one, you see. So for example, if you consider x sub 1, it will be 1/2, then x sub 2, it will be 3 over 4, x3, it will be 7/8, and so on. So you will have that the minimal element of this set, it will be exactly x sub 1. Will be exactly x sub 1. So in this case, the minimal element will be also inf of this set. Is it clear? Is it clear?
Yes, yes, it's clear.
Thank you. So the second statement of 4.2 is that the sup of this set M is 1. Okay. So here for you, I want to show how we can use the definition of the least upper bound for a set. In this case, our set M is defined in the exercise number 15, case 1. So you see that first of all, all of the members of the elements of our sequence are less than 1. Clear?
Yes, clear.
Yes. So at least, you see, if you have the interval 0, 1, and if I take the upper bound, which is 2, all the elements are less than 2. It's very good, but for the set 0, 1, 2 is not the least upper bound. So, but in this case, all the elements are less than 1. It's clear. So we can claim, I hope we can say that we know that the upper bound, that 1 is an upper bound for our sequence. Okay, the first step. Now, if we take the definition of the least upper bound, we have to fix epsilon strictly positive. So I write here in this file, I write, now let us fix epsilon greater than 0. So for any number, you see, you want epsilon to be 1/2, or epsilon to be 1/3, or epsilon to be 1/1000, you can. So for each, but first of all, we fix this epsilon. So I take some small number, okay? And what do you want to show? That we can find some element x sub n from our sequence, from our set. It's, in this case, it is the same thing from our sequence or from our set, such that xn is greater than 1 minus epsilon. Please please see the definition of the least upper bound. So, in this definition, page 90, okay, for each epsilon greater than 0, there exists an element x from our set such that, from our set such that x is greater than d minus epsilon. So, what do we want? We want to find x sub n from our sequence such that x sub n is greater than 1 minus epsilon. In fact, what do we need? We need to find n, natural n, such that the element xn is greater than 1 minus epsilon. So you fix epsilon, and then I want to find such n such that x sub n is greater than 1 minus epsilon. Is it clear? Due to the definition.
Yes, it's clear. Yeah.
It's clear. So if it is clear, then this means you see in the formula the general formula for our general term x or x sub n. You have that x sub n is 1 minus 1 over 2 to the power n. Okay? So, what do we want in order to find this n is to solve an inequality. So I write 1 minus 1 over 2 to the power n is greater than 1 minus epsilon. So I repeat, because I know that x sub n is 1 minus 1 over 2 to the power n, and I have this inequality. Is it clear?
Yes, it's clear.
Really? For all? Or only for you, Eric?
I'm not
Yes,
sure.
we're all
I'm not sure they were gonna respond.
Yes? Yes? Onya, est-ce que c'est clair? Onya, est-ce que c'est clair? Okay. So then you have this inequality, and you have from this inequality that epsilon have to be greater than 1 over 2 to the power n. You see this? So 1 disappears, we change the signs, and we have the inequality that epsilon is greater 1 over 2 to the power n. Yes or not?
Yes.
Really? Eric, clear?
Yes, for me it is.
So if I have this inequality epsilon greater than 1 over 2n, then I have the 2 to the power n is greater than 1 over epsilon. You see, the last step is to take the logarithm, for example, to the base 2, in order to have that. You see, from this inequality 2 to the power n greater than 1 over epsilon, normally we have that n is greater than log to the base 2 of 1 over epsilon. N is greater than log to the base 2 of 1 over epsilon. But you see why we have to write in this way? Because n the natural number. So if I take the integer part of the value log 2 of 1 over epsilon, and then I add 1, then I will have a natural number such that all my inequalities hold true. So if I take some epsilon, I fix it, then there exists some x sub n from my set, from my sequence, which is such that x sub n is greatly than 1 minus epsilon. This means that 1 will be the least upper bound of my set. Is it clear or not?
Yes, it's clear.
Clear. The answers, not only you. Clear.
Yeah, it's clear.
Clear. Thank you.
Yes, that is clear.
Okay, so you see, I don't know, maybe in your school or somewhere, here in Russian, we usually use this notion integer part. But maybe you know the terms something like flow function. Here we do not use this, so please, no. If you want, you can use also flow functions and so on. But usually we use the brackets like this in order to note the integer part of a function. So the integer part of a function, for example, if you take 2.535, then the integer part of this number will be 2. So it will be the largest integer less than or equal to your to your number. If you take the integer part of some x. So I repeat, the integer part of x. Now I take only the positive x. So the largest integer less than or equal to x will be the integer part. So roughly speaking, if you take 1.3567, so the integer part is 1 without any digitals, without point and so on. So only the integer. Is it clear?
Yes,
Clear?
it's clear.
Clear. So very good. Now we turn to the so-called complex numbers. So please take the file of the seminar number 2. Please find this. It's good or not? Is it good?
The second file, correct?
Yes, second file. Seminar number 2, complex numbers. Please open the file. Can you see the file?
Yes, I can see it.
Yes,
Yep.
sir.
Yes.
So we can start. So here I write for you some short introduction in order to explain why we dealing with these complex numbers. You see, the reason is for today, evidently for today is rather clear. If you take the quadratic equation a x squared plus b x plus c equals 0, I hope that you know that there are two roots of this equation, and these roots are given by the formula 1.1. So, first of all, from your school, I hope, from your school, you know that if, can you see the formula 1.1?
Yes.
Yes.
Yes. So, that, from your school, I hope you know that if b squared minus 4ac is positive, or maybe it can be 0, we have no problems. We
can find the solution.
we can find a solution, and these two solutions, if you want, will be real numbers. But the question is, if b squared minus 4ac is negative, so as for the real numbers, we have no real solutions to our quadratic equation. It is not good, at least for the mathematicians, it is not good. So we want to find a solution. So as for, if you turn your page you can see that if b square minus 4ac is strictly greater than 0, the first picture is that we have two distinct real roots. If this guy b square minus 4ac is really 0, then you have that the graph touches the real or the x-axis. So in some way we have one root, but we have two roots which are equal one to another. So in this case it is very, very good. But if our b square minus 4ac is strictly less than 0, then we have that our graph is over the axis 0x. You see, it's the third picture. Now the idea was, or for us, the idea is to introduce some special number, which is square root of -1. And I say to you, and you believe me, that this number exists. You see, we say that the number square root of -1 exists. Then we can rewrite our solutions, our two solutions, our two roots to my equation x squared plus bx plus c equals 0 in the form 1.2. So here, you see, we have something strange because we have a plus minus b multiplied by the square root of -1. So here we have the reason to introduce this number. So now, as for the quadratic equation, and also if you want for cubic equation, you have all the roots of this equation. So this is the reason. So I repeat, it is only a short introduction to the subject in order to understand why we have to study these complex numbers, because in all the physical disciplines you will have a lot of examples of the utilization of these numbers, because it is not possible to avoid these numbers. Then you turn your page, and from this short introduction we pass to some formal definition. In order to denote our square root of -1 in the mathematical literature, I underline, in the mathematical literature we use the letter I. But you have to know that as for the physical books and maybe the engineering book literature, you have you have another symbol in order to denote square root of minus y, it will be j. But for us, I repeat, as in the mathematical literature, we use I. Okay? So now, the second definition. The second definition, I want to define a number. I want to define a number a plus bi. Here, I repeat, I is the square root of minus 1. So in some way, you will see in your future studies, in some way you have a vector. Maybe it is nothing for the moment, but in fact, you have two parts which are very different one from another. So A and B are the real numbers, but you see that you add to a real number something which is strange, because square root of minus 1 is a strange thing. Then A, which is a real number, is also known as a real part of a complex number Z, and B, which is also a real number, is known as an imaginary part of your complex number Z. And the notation is here. So B im Z and A is re Z. So you see, if you take B equals 0, then you will have a real number A. This means that any real number is in fact a complex number. Is it clear?
Yes, sir.
Mm-hmm.
Yes. So this is only for the definitions. So we have some definitions we will work with. So now we turn the page and we go to the definitions and notation slide number 2. So S4, you see, as for the real numbers, we make use of the notation capital R. As for the complex numbers, which is clear, we will use the notation capital C. You can see this, page 5. So now, the equality between the complex numbers. If you have two complex numbers, A plus DI and C plus DI, then we say that these numbers are equal if and only if A equals C and B equals D. So the equality between two complex numbers means that their real part and their imaginary part are equal. I think here there is no problem, and you can accept this. Now the useful thing. If I have it's the second or the definition, page 5. So if I have my complex number z a plus bi, then I can define the conjugate of z. The conjugate of z, it is not very difficult. I will change my plus di by minus di. So the conjugate number to the number z is a minus di. Only this. The notation for this conjugate z is z bar, or maybe in physical literature we can also see that this number is called z star. But in our work, we will use the notation z bar. Okay. Now, if you turn the page, why I want to say that you can consider your complex number as a vector. Here on the page 6, it's a classical picture. Here you have Argand diagram. So if I have my complex number, then I can have a point on the plane y, x. So the imaginary part of my complex number is when you plot, for example, the graph of some function. So you have y and you have x. Here, if I take as the axis y, my imaginary part, and as for the axis x, my real part, I have a point. Can you see these points on this diagram? I hope it is clear. So I take one axis as my imaginary part, and the second one, oh no, like this. And the second one is my real part. So you know, for example, your imaginary part, you take some point on your imaginary axis, and you have your real part, you have some point on your real axis. So you can find your complex number of on this plane, because in fact you have a complex plane. Is it clear? Good. Clear. So we will not use, in fact, we will not use really this Argand diagram, but in order to understand in our further studies the modulus or the argument of our complex value, in fact, we will use this diagram. So now, page 7. Page 7. This will be a last exercise before the break. Okay? So page 7. The exercise number 5. So we want to calculate the sum. I to the power 17 plus I to the power 18 plus I to the power 19 plus I to the power 20. So, first of all, I recall you that I square is minus 1 by the definition. Then, if you want, I to the power 4 is 1. Clear?
Yes, sir, it's clear.
Clear. Then, you see, if I take I to the power 17, it will be I to the power 16 multiplied by I. But I to the power 16 is 1, because I to the power 4 is 1. Yes? Okay? Clear?
Yes, sir, it's
Then you see, if I take I to the power 18, it will be I to the power 17 multiplied by I. Then it will be minus 1. And in the same way, I can find I to the power 19 and I to the power 20. That is the sum of these 4 terms is finally 0. You see? So if somebody asks the question, is it really the fact that the sum of some complex values is always a complex value? The answer is no. Here you see an example of such a situation. You have some complex numbers, and the sum of these numbers, of these complex numbers, is a real value. Is it clear?
yes, sir.
Okay, so we have a break for 10 minutes. Okay? 10 minutes break.